This is one of my favorite statistics jokes. Why is that woman scowling at me? Do I know her? If she loves you more each and every day by linear regression, she hated you before you met. Anyway, so today we're actually going to look at some applications that aren't really linear, but how can we use linear regression tools to analyze them? So, this is an actual article I found from NPR, February 2014. You should always order the bigger pizza. So, an engineer went for pizza and ordered a medium instead of a large, even though he wasn't very hungry. When asked by his friend why he did that, he explained that the medium was more than twice as big as the small. This inspired his friend to collect data for 74,476 prices from 3,678 pizza places. And that was around the country, and he used Grubhub Seamless to get the data. So this is real data. And what I did is I put together the averages showing the largest number of square inches of pizza you could get for a given price on average. And here is the model. In your notes, you have the actual data, but here's the regression. So you can see the scatter plot here in the line for the model. So how would we describe this relationship using Duff's? Well, the direction is positive or increasing. Unusual features, I would say none. Now, you could say, well, it's curved, but then I would tell you, well, that's actually part of the form. It's curved upwards, definitely nonlinear. It looks really good, and if you look at the r squared, which is related to r, it's at 97%, which means r is even higher than that when you square root it. But I can definitely see curvature there. So strong but not linear. So r is not so meaningful when it's not a linear relationship. So let's go ahead and double check this by doing a plot of the residuals, which I did right there. So go ahead and copy that into your notes. And does that look like random scatter? No, it's inappropriate because there's a very strong curve pattern in the residuals. In fact, it looks like a quadratic or a y equals x squared pattern. So we only learn linear regressions in this class. We're not going to do quadratic or anything else. But that doesn't mean we can't examine nonlinear relationships. So we can sometimes transform nonlinear relationships to determine if there's a linear relationship between the new variables. So we could apply different functions, including a power, a root, which is really another flavor of power, or a logarithm to a quantitative variable. And this is called transforming the data, which is what this lesson is about. So to me, the pizza pattern from the residuals looked very much like y equals x squared. So let's undo the square by taking the square rooting, or taking the square root of the pizza area. So I had price here was x. Pizza in inches squared was here. So I'm going to take the square root of that area. And now you can see my new model. Here are my coefficients, and my r squared is actually 100%. Can't beat that. But we always want to check the residuals. And when I plot the residuals here, it actually does look like random scatter. So I'm going to go ahead and describe the relationship again with my new model, which is the direction is positive or increasing from the previous graph. There were no unusual features. The form was linear this time with no curvature. And it was an incredibly strong relationship. R squared was 100%, so that means r is the square root of 1, which is 1. The linear fit is appropriate because of the random scatter in the residual. So we can also use this to make predictions, and you have to be a little careful because it's not exactly a linear fit. In fact, our model from here, remember I was using the response variable was the square root of the area. So that's what I have on the left here, equals 0.19365 plus my coefficient of price. All right, plus that times the coefficient of price. So if I want to do figure out area for $30, I would go ahead and put the 30 in for price, and I get 51.1172. And since I'm trying to find area and not square root of area, I would square that. and I get 2,613 inches squared. By the way, what other transformations could we have tried with the pizza example? I could have, instead of taking the square root of area, I could have tried squaring the price. So that's one other thing I could look at, but there's some other stuff I can show you too. So these types of relationships are called power models, where you have y equals some coefficient times x to some power, where a is the coefficient and p is the power. Some real-life examples of power models include volume, which is, let's say we did a sphere, or, a sphere is fine. It would be some coefficient times the radius cubed. And in fact, for a sphere, it would be 4/3 pi r cubed. For weight, if I was looking at it in terms of gravity, the official formula is the universal constant for gravity right there, times mass 1 times mass 2 divided by radius squared. So if these two are constant, you could say, oh, weight depends on how far you are from the center of the Earth. So actually, the further you go away from the Earth, the less you weigh. All right, so there are two methods for transforming the data to achieve linearity. One, you can raise the values of the explanatory variable x to the power and plot the points x to the p, y. Or you can take the pth root of the values of the response variable y and plot the points x comma pth root of y, which is what we did in the pizza example. So if we know the value of p because of the type of relationship where it makes sense, then that's what we should do. However, if we don't know p, we can actually use logarithms to transform a linear relationship. So how does that work? Well, let's take a look at the power model, and we're going to take the logarithm of both sides. I'm doing log base 10 just to keep it simple. And you might want to remember some of your algebra 2 here. Log of y is equal to log of a times x to the p. When we have products and logs, we can break them up into addition. Log of y equals a plus log of x to the p. And you might remember that exponents in logs can come down and become a coefficient in front of the log, which is what we get there. So log of a is just a constant, and that would be your intercept. Log of x, well, that's our new variable, and p would be the slope, and log of y would be our new response variable. Now we reran the regression on the pizza data using the logarithm of area and the logarithm of price. So let's go ahead and see if we can kind of work backwards and see what the actual relationship is. So I have log of area equals this plus 1.99 times the log of price right there. And what I can do is I can move the log of price over, all right? And when you subtract two logarithms, again, reviewing algebra 2, that's the same as dividing. So I'm just going to say that the log of area divided by price is 0.4774. Oh, you might not have noticed that I made the 1.99 here into the exponent right there. So make sure you notice that too. Now, if I put a 10 as a base on both sides of this undoes the log because this is log base 10. So 10 to the log base 10 of something is just whatever's in the parentheses. And then 10 to 0.4774 is actually 3. So this equals 3. And then I can multiply both sides by price to the 1.99 power, and that is the equation I get. So having done my regression with logs of both variables, I can work backwards and say, oh, here's my equation. Now, just out of curiosity, how does that compare to our square root formula? Well, that was square root of the area is 1.6974 times price. If I square both sides, I get something really close to what I had here. 2.89 times price squared is 3 times price to the 1.99. So they're slightly different because they were obtained in different ways. Now, let's go ahead and look at exponential relationships. And these are usually things associated with population growth, compound interest, radioactive decay, and carbon dating, which is actually just a special radioactive decay. So, I went ahead and got data for the world population, and these are the years when we hit different billion marks, starting in this last century. So 1927, we hit 2 billion. 1960, 3 billion. 74, 4 billion. So if you look at it here, this is the fitted plot for the linear model, where I just say, okay, multiply the year by something, and in this case, 60,635, and then subtract this number, and that gives you the population. The R is very strong because R squared is 95.28. If I took the square root of 0.95, it's actually higher than 0.95. But the problem is that there's a pattern in the residuals. I mean, clearly there's a linear pattern right here. Looks like that's a little bit of an outlier. Well, how is growth supposed to behave? It's supposed to be exponential. So since population is known to grow exponentially, basically, here's what we're going to do. When an association follows an exponential model, we do the transformation by taking the logarithm of just the response variable. If a variable grows exponentially, its logarithm grows linearly. Now let's go ahead and look at the world population, which definitely falls into exponential growth. And in 1927, so now I have the logarithm of the population. Instead of being 1 billion, the log of pop is 6.30, actually 2 billion, 6.30103. So these are the different logarithms of the population. And when you look at it, the fitted model looks much better. And, well, we can probably say it's not a lot of data points. We can probably call that random. So using Duff's, we describe the relationship as positive or increasing, no unusual features. This form of the transform variable is linear, and it's strong because our R squared is 99.34%, which means R is 0.997. And a linear fit is appropriate because of the random scatter in the residual plot. It's really hard to say if there's any pattern going on right here. So which transformation should you use in general? Well, if it logically fits one of the models based on relationships and the correlation and residual plot look good, well, use the model that makes sense. Otherwise, if you're kind of just trying different things, choose the model with the most random scatter on the residual plot. Now, if you've got more than one to choose from, then choose the one with the highest coefficient of determination, or R squared. So let's go ahead and revisit our pizza example again. Logically, we should say that your area, the amount of pizza you get, should be linear to your price. It should be proportional. But the problem is, while our R was strong, there was definitely a pattern in the residuals, so we need to reject this model. Well, let's go ahead and look at the different plots of residuals for different models. This was the one we were just talking about, and this one won't work. So I would say the most random one we have is right there. And that was when we had the square root of the pizza in terms of the price. And that was this equation right here. Last but not least, let's go ahead and look at a table of the different models and their R squared. And the one with the highest R squared is, again, the square root of the area one. So is our decision confirmed by the R squared values? Yes, it is. The model with the most random scatter on the residual plot also had the highest correlation.